All right, one other application of momentum and energy conservation that I'd like to show is radioactive decay process. And so this is something we'll be doing much more of in Physics 2.8c, but the important thing about radioactive decay is that this is happening at the level below the level of molecules. And in terms of size, what this means is that there is essentially no friction, and so this is an elastic interaction in which momentum and energy conservation are both valid. However, if we have a particle that starts out with no initial momentum and no initial energy, and then it decays, we have to ask ourselves the question, where did that energy come from? It seems like it didn't have any energy. Well, it turns out that the energy comes right from the mass. And so here we can see that if we call Q the nuclear binding energy, we can think of it as being a form of potential energy. And that potential energy can be converted into kinetic energy if the mass becomes less. Okay, and so in this case, delta M is the amount of mass converted to energy. So this is depends on Einstein's principles of special relativity, that E equals mc squared is basically what this is telling us. But here, this is the difference in mass between a larger particle and a smaller particle during a radioactive decay process. So let's just look at this example up on the board in which we have a thorium nucleus, which is unstable and tends to want to decay, and so it'll decay by means of ejecting an alpha particle. Now, an alpha particle is just a helium nucleus which has an atomic mass of 4. And so what we'll end up with then is the thorium-227 will decay down into radium-223. And the difference in mass is that 4 atomic mass units that it is losing by means of the alpha particle. And so if we come back down here, we see that now the radium is our M prime here. This is the mass of the radium. M alpha is going to be our 4. Okay, now that's 4 atomic mass units, so we'd have to convert that into kilograms if we actually wanted to get an expression for Q in joules. But here, just by solving the momentum and energy equation simultaneously, what we end up getting is that the kinetic energy of the alpha particle is equal to the vast majority of the total energy that comes from the nuclear binding energy. And so the nuclear binding energy is what delivers this energy, you would think perhaps equally to both masses? No. It prefers the smaller mass. And this is the only way to conserve momentum and energy at the same time, is to give most of the energy to the alpha particle. So this is the kinetic energy of the alpha particle in terms of the total available energy, and this was energy that was originally came from the difference in mass, that mass being converted to energy. And so for this particular example, the radium isotope that we're looking at has an atomic mass of 223, and the original thorium nucleus had an atomic mass of 227. So that gives us 0.982 times Q total as the kinetic energy of the alpha particle. So what that shows us here is that 98.2% of the energy that was available in this reaction went into the alpha particle. So the alpha particle goes flying out there with incredible speeds, not only because it has a small mass, but also because it has a huge velocity. Okay, and so that means that the velocity has to be even bigger because it has to take the majority of the kinetic energy with it. So 98.2% of the energy from the nuclear reaction goes into the alpha particle, and only 1.7%, 1.8% of the energy goes into the radon, okay, or the radium. So this is why radioactive decay is so dangerous to people, is that it's not so much that you have a particle hitting you, it's that the particle is moving really fast. So if this particle hits me going this fast, I'm not worried about it. But if somebody put it in a big slingshot and then fired it at me, then I would be a little more worried because it would have more momentum when it hit me. And if most of the energy from the interaction goes into the smaller particle, it'll just rip right through you. And that's the reason why nuclear processes create energy in the form of small particles that are like little tiny bullets that can go right through you. And this is what causes the damage. Okay, and so I wanted to illustrate this with a few masses here. And these masses, I don't know if we'll be able to keep this on screen or not, but I'm going to drop all four of these and I'm going to have it hit the table, and then let's see what happens to the smaller mass. So try to follow that as we go here. Here we go. Oh, it just flew off at very high velocity. The rest of these were left behind. But that little tiny red ball went flying, and I hope that I'm going to be able to find it later. But that is an example of how most of the energy from an interaction that involves masses that are not the same as each other tends to prefer the smaller mass. And so that is the mass that gets the majority of the energy. All right, so that's the last subject that I wanted to cover from the chapters that you'll be seeing on the midterm. Okay, so remember that's chapters 5, 6, 7, 8, 9, 10, and then we'll have a little bit of chapter 13. Okay. And so then those will be the subjects for the exam. And I'll spell that out for you one more time in an announcement that I'll send out later today. So we're drawing the line here for the midterm. And what I wanted to start out with next is chapter 14, which is simple harmonic motion. Okay, so simple harmonic motion then is the first subject again for for midterm number 3, and is the subject of chapter 14. From there, we'll go to we'll go to fluid mechanics, which is an earlier chapter that we'll look at soon. Okay, so with simple harmonic motion, what do we have? Well, in order for an object to move with simple harmonic motion, we must have a repeated motion. So this motion then has to repeat itself in some kind of a well-defined way, so that once we've seen one cycle of the motion, we know what to expect from then on. So here we have a mass on a spring. So if I let this thing move up and down, what we have is simple harmonic motion. Okay? And so this is just a repeated motion. Once I've seen one cycle of the motion, I've seen them all. Here's another example of simple harmonic motion. This is called a simple pendulum. That was a mass spring system, as you probably already know. Here, with a simple pendulum, this is another kind of simple harmonic motion. Notice again, a repeated motion, and so that once we've seen one cycle of the motion, we know what to expect from then on. And so there are many other examples of simple harmonic motion that we'll talk about as well. But for simple harmonic motion to occur, we must have a repeated motion with one, a restoring force, okay, so what do I mean by a restoring force? Well, in our mass spring system, we have a spring with an unstretched length, x equals 0, and we pull it a certain distance away from equilibrium, assuming no friction on this surface. At this distance x away, Hooke's law, which we've already looked at, shows us that the restoring force is equal to minus kx. And so this then is the restoring force that tends to bring the system back toward equilibrium. What if it overshoots equilibrium and starts to compress the spring? Well, when it gets to this point, then we would have a displacement x that's in the negative direction, but the restoring force would still be in the opposite direction from the direction of x. And so, in other words, this system is never happy unless it's at equilibrium. And if it's not at equilibrium, there is a force that tends to bring it back toward equilibrium. Now, if it weren't a restoring force, if, say, I pulled it this way and that made it want to go more in that direction, then it would never come back. So you have to have a restoring force to keep it moving about some equilibrium position. And so that's one example of a restoring force. Another one would be found with the simple pendulum. So in this example, although it looks like a completely different problem, it still has the same basic qualities that we use to define simple harmonic motion. And so if that angle is theta, then there's going to be a certain component of the force that is going to be taken up by the tension in the string. That would be mg cosine theta. But there's also a component of the force, just like on an inclined plane, that tends to bring it back toward equilibrium. So this is equilibrium now. This is theta equals 0 equilibrium. And the restoring force then, F, we'll call it restoring, is minus mg sine theta. Okay, now this restoring force is a function of theta. So it will change as theta changes, but the restoring force nevertheless is acts to bring the system back toward its equilibrium position. Then it can overshoot that position, come back up to this point, then the restoring force will be that way, tending to bring it back toward equilibrium in the opposite direction. In just the same kind of a manner as what we saw here with the mass spring system. So this is called a simple pendulum. And this is our standard mass spring system. Okay, so once we have established that, we can talk a little bit more about how this simple harmonic motion could be plotted. Let's say that we have a displacement x, in this case, for the mass spring system. That's the distance of the mass from equilibrium. And we plot that versus time. Okay, so that kind of a plot then is going to look like this. It's going to go from positive to negative as the spring oscillates back and forth. So this maximum distance from equilibrium we could call A, the amplitude, maximum amplitude. and then it would oscillate between plus A and minus A. And it would go through a complete cycle in an amount of time that's equal to the period. So this is something you did in our first lab. You figured out the period for a simple harmonic oscillator, for a couple of them in that first lab. So this is the time for the system to go through one complete cycle. So this is not a wave. This is just the plot of the simple harmonic motion as a function of time. So it goes across like this from A to minus A, and then back again. As it does this, this is positive A, this is minus A. These are the 2 points at which it crosses. And so it just keeps repeating this cycle over and over again. Okay, now if I were to displace the spring by a smaller amount, there we go, what we find is that the amount of time that it takes to go through one complete cycle is the same as if we displace it through a larger amount. So this is kind of interesting, that I could pull it by more, and it still takes the same amount of time to go through one complete cycle. And this is also approximately true for our simple pendulum. If I let the simple pendulum go, and this has to be between what we call small angle limits for this to work, but if we keep it less than, say, 10 degrees, and I displace it by a certain amount, then the amount of time that it takes to go across and back is the same if I displace it through a smaller amount and let it go back and forth. So associated with this, then, we say that the system has a natural period and therefore frequency of motion. I'll abbreviate simple harmonic motion by SHM. We have 4 simple harmonic motion. 1, we must have a restoring force. We saw that before. But we also must have a natural period to the motion. And this also means a natural frequency. Now, why does period imply frequency? Well, period is the time that it takes for the system to go through one complete cycle. And so we can set that equal to the inverse of the frequency, where the frequency is equal to the number of complete cycles that the system goes through in a second's worth of time. And so this has units of hertz. So hertz then is a cycle per second by definition. Okay, so for example, let's say that the period of motion of this mass spring system here is down and back about a half a second, let's say. Down and back, down and back. Let's just say that's right. For half a second, then the frequency would be 1 over a half, or 2 hertz. So 1, 2. Actually, it'd be probably more like a third of a second here. 1, 2, 3. So in this case, let's say that the period is 1/3 of a second, then the frequency would be 1/1/3, which would be 3 hertz, which means that it would go through 3 complete cycles in 1 second. So does that make sense? If it takes 1/3 of a second to go through 1 complete cycle, then that means that it would go through 3 complete cycles per second. Okay, because you're breaking that second up into 3 little chunks where we have a complete oscillation in each of those little third of a second. And so therefore you get 3 complete oscillations can fit into that 1 second time interval. Okay, and so that's the reason why once we know the period, we know the frequency, and vice versa. Okay, so either one, if we knew the frequency, then we could immediately calculate the period by just taking the reciprocal of either one. So we have maximum amplitude, and we've also established the fact we have this natural period and frequency to the motion of an object that is experiencing this restoring force and going through simple harmonic motion. So the next question is, if this is the plot for a larger amplitude, then that means that if we go to a smaller amplitude, it'll have a similar plot, but with just smaller max-min values. But it'll still have the same period to the motion. Okay, and so this is what is the basic property then of a simple harmonic oscillator, is that, and this represents then for different values of the initial amplitude, the same shape plot, but with different max-min values for the amplitude. Okay, and so the next question then is, well, how do we express this? This looks like some kind of a sine or a cosine wave. Well, we can express that x versus t plot in the following way. We can say that x equals a times the cosine of 2 pi over the period times the time. And this, of course, assumes that it starts out at x equals a when time equals 0. And so why does this work? Well, because if the time is 0, then the cosine of 0 is 1. 1 times a is a. So that puts us here. What if the time t were equal to the time that elapses on the horizontal axis is equal to the period over 4? Okay, so that would be 1/4 of the period. That would bring it back to the equilibrium position. So that would be like this. It would start out here at x equals a. Then after 1/4 of a cycle, it would be here. It would be at 0. And so that would put us here on our plot by the time that it's moved back to the equilibrium position. And then it would overshoot that equilibrium position. Okay, so with t time equals the period over 4, we would get x equals a times the cosine of 2 pi over the period times the period over 4. So that would be a times the cosine of pi over 2. But the cosine of 90 degrees is 0. Okay, so that brings us back to the equilibrium position. What if t, the time, elapsed equals the period over 2? Well, then we've gone period over 4. We go to this point, which is the period over 2, where x equals minus a. So now we're here, and we plug into this expression, a times the cosine of 2 pi over the period, it's a period over 2. And so that gives us a times the cosine of pi. The cosine of pi is minus 1, so that just gives us minus a. So this is where we are here. So this is the time equals the period over 2. This is the time equals the period over 4. What about when we get to this point? Well, you might be able to guess that that would occur when the time equals 3/4 of the period. And so it goes 1/4, 2/4, 3/4. Now it's on its way back out again. And so for the time equals 3 times the period divided by 4, we would have x equals a times the cosine 2 pi over the period times 3t over 4 for the time. So that would give us a times the cosine of 3 pi over 2. But the cosine of 270 is also 0, so that gives us this value. This is 3 period over 4 for the time. And then finally, when we get to the period, then it's the cosine of 2 pi over the period times the period, which is just the cosine of 2 pi, which is 1. 1 times a is a. And we're back to this position and ready to start over again. Okay. And so what we can do then with this expression, since it looks like it works and allows us to write x as a function of time rather than as a function of theta, but here we've got units of 1 over time times time. So this will actually be in radian measure. And it will not have any units because the time units will cancel out. And so the only units left then are the units for angle, which technically aren't really units anyway. Okay, but we keep track of them so that we make sure that our calculator is in radian mode for this kind of a problem. Okay, so once we have this expression, we can write this in a slightly more compact form by defining our angular frequency, omega, to be equal to 2 pi over the period. Or that would be 2 pi times the frequency. Then we can write x as a times the cosine of omega t. So this then becomes our working equation for plotting out the x versus t motion of an object that is experiencing simple harmonic motion.